Assalamu alaikum and very good evening. In this video, I am going to derive the elasticity of substitution for Cobb-Douglas production function, but this time I'll give you a numerical example. In video number 464, I discussed the general derivation of elasticity of substitution for both Cobb-Douglas and CS production function without a numerical example, but in this video I'm going to do that with the help of a numerical example. So first I will share with you the schema of presentation, and I'll calculate MRTS for Cobb-Douglas production function, and then I'll make derivation of elasticity of substitution for Cobb-Douglas production function, and finally I'll give the numerical example of MRTS and elasticity of substitution under Cobb-Douglas production function. And after that, I'll conclude this presentation. So, how can we derive marginal rate of technical substitution for Cobb-Douglas production function? Let us suppose the Cobb-Douglas production function is given by the following, where y is a function of x1, x2, and that is equal to a x1 raised to power alpha, x2 raised to power 1 minus alpha, where we assume that the constant a is equal to 10, alpha is equal to 0.3, and 1 minus alpha is equal to 0.7. We also know that marginal rate of technical substitution of x1 for x2 is equal to the ratio of the marginal physical productivity of x1 divided by marginal physical productivity of x2, and we also assume that x1 is labor input and x2 is the capital input. So if you take partial of y with respect to x1, then that is equal to this is easy, and if we simplify, then we have this alpha times a times x2 divided by x1 whole raised to the power 1 minus alpha, and this is the marginal physical productivity of labor x1. Similarly, the marginal physical productivity of capital denoted by x2 is equal to the partial derivative of y with respect to x2, and we have this is the marginal physical productivity of x2. It follows that the marginal rate of technical substitution between x1 and x2 is equal to this equation, and we have in the numerator alpha a x1 raised to power alpha minus 1, x2 raised to power alpha 1 minus alpha, and the denominator is 1 minus alpha times a into x1 raised to the power alpha, x2 raised to the power minus alpha. So we cancel out some of the things with each other. For example, this a cancel out with this one, and this x1 raised to the power alpha cancels with this x1 raised to the power alpha, and this 1 minus alpha, this minus x2 raised to the power minus alpha cancel with this x2 raised to the power minus alpha. So finally we have alpha divided by 1 minus alpha, which is constant, times the ratio of the two inputs, that is x2 and x1. So alpha divided by 1 minus alpha is constant and x2 divided by x1 is the input ratio or the factor ratio. After this, we will derive the elasticity of substitution for this Cobb-Douglas production function. Since marginal rate of technical substitution of x1 for x2 is equal to alpha divided by 1 minus alpha times x2 divided by x1, so delta or change in marginal rate of technical substitution is equal to alpha divided by 1 minus alpha times delta x2 divided by x1. So we also know that the elasticity of substitution is given by this formula, that is the percentage change in the input ratio or the factor ratio divided by the percentage change in the marginal rate of technical substitution of x1 for x2, and that is equal to a change in the factor ratio divided by change in the marginal rate of technical substitution times marginal rate of technical substitution divided by the input ratio. So putting these values, we may cancel out some of the factors from this, and finally we see that delta x2 divided by x1 is cancelled out with this delta x2 divided by x1. This alpha divided by 1 minus alpha is cancelled out with this alpha divided by 1 minus alpha, and this input ratio is cancelled out with this input ratio. So we have 1. So elasticity of substitution is equal to 1 for the Cobb-Douglas production function. Hence, the elasticity of substitution for the CD production function is equal to 1. Now let me share with you the numerical example. We have seen that marginal rate of technical substitution of x1 for x2 is equal to this, and change in marginal rate of technical substitution of x1 for x2 is equal to this. So if you plug in the numerical values of a equal to 10, alpha equal to 0.3, and 1 minus alpha is equal to 0.7 in the Cobb-Douglas production function, then we get this. In that case, marginal rate of technical substitution is equal to 3x1 raised to the power minus 0.7 x2 raised to the power 0.7 whole divided by 7 x1 raised to the power 0.3 x2 raised to the power minus 0.3, and if we simplify this, we get 3 by 7 times x2 divided by x1. So this is MRTS, and delta MRTS would be 3 by 7 delta x2 divided by x1, that is change in the input ratio. So if you put these values in the formula for elasticity of substitution, then sigma is equal to delta x2 divided by x1, which will cancel out with this delta x2 x1 in this denominator. Similarly, this 3 divided by 7 here in the numerator will cancel out with this 3 by 7 in the denominator, and this input ratio of x2 to x1 will cancel out with this input ratio of x2 to x1 in the denominator. So finally the value of sigma, that is elasticity of substitution, is equal to 1. So in both cases, in numerical example and in the generalized form of Cobb-Douglas production function, the elasticity of substitution is equal to 1. I hope this is easy and very convenient to understand, and I hope this is of help to you. So if you like this video, kindly subscribe to the channel, and don't forget to click on the bell icon so that you could get regular notifications about other videos that I am going to upload for you very soon. Thanks for watching this video, and kindly share various videos of this channel in various WhatsApp groups and on social media, so that this could reach to the